Welcome back, folks. Here we see the three primary temperature scales, and I want to tell you a little bit about where they each come from, and then take a look at the differences between each pair of them. If I start with Fahrenheit, which is sort of a very arcane system, Fahrenheit came into existence with the particular size of degree it has because of the difference between human body temperature and the freezing point of water. At least as this thermometer was initially being made, the way that this was done was that the human body temperature was assigned a temperature of 96 degrees Fahrenheit, freezing point of water 32, because that was all with reference to a mixture that was 1 to 1 to 1 water, ice, and NH4Cl, which was referred to by the scientists as brine. This was declared to be 0 Fahrenheit. And I want you to notice something here. The distance between those two degree markings is 32. The distance between these two is 64. Notice that those are powers of 2. This is 2 to the 5th. This is 2 to the 6th. And so the basic, incredibly idiosyncratic reason why this scale was built the way it was because if you took a tube of mercury, marked where the brine froze, marked where the water froze, and marked the body temperature of the experimenter, you could go in and start subdividing. Even for as much as we love to use powers of 10, powers of 2 are a lot easier in the moment to do because you simply say, here's a spot, bisect. That's much, much simpler to do. And if you do that 3 times, bisect, and then bisect, bisect, the result is that you wind up with 16 lines, then 32 lines, then 64 lines in between the original 2 markings. And so that's how the degree in Fahrenheit was defined. It was all about making the tool. On the other hand, the Celsius scale here is defined entirely based on water, and it's built to look a lot more like something from the metric system. In Celsius, we assume that 0 degrees Celsius is the freezing point of water. And then 100 degrees Celsius is the boiling point of water. By the way, over on this scale, that boiling point turns out to be 212 Fahrenheit once you keep making more and more markings with the same distance between them. Now, because of the fact that it is 100 gradations, 100 markings between 0 and 100, between freezing and boiling point, Celsius is also frequently referred to as centigrade. So take a look again at that 1/100th right there. Every degree Celsius is 1/100th the distance between freezing and boiling water. Now, as you well know, there are temperatures well below the freezing point of water. There are all sorts of things that are colder than that. Dry ice, liquid nitrogen, liquid helium. And in fact, there are things much, much colder than 0 Fahrenheit. And so we mentioned at the end of the last video that this would be a problem for us. If I've got a proportionality between volume and temperature, or pressure and temperature, I can't have temperature go negative. And so the scale that we use whenever we're dealing with gases is kelvins. And the way Kelvin works is this. First off, 1 degree Celsius is the same thing as 1 Kelvin if you're talking about a temperature change. In other words, if the temperature goes up 40 Celsius, it went up by 40 Kelvin. However, this scale has a very different offset. Instead of water freezing at 0 Celsius, we now would say that water freezes at 273.15 kelvins. And the reason for that specific number is that if I go down to negative 273.15 degrees Celsius, I reach 0 Kelvin, which is the temperature at which all molecular motion stops. If temperature is meant as a measure of kinetic energy, you can't have less than 0. So that's what we set as the 0 of our scale. Now, particularly because of the offsets being different for each one, the fact that 0 is defined as being a different place for every temperature unit, converting between them isn't as simple as it is for something like pressure or volume units. If I have 0 pressure, it doesn't matter what unit I'm in, it's 0. Same thing with volume, same thing with distance. Temperature, it's a little weird, so we have to use a bit of algebra. Let's start by comparing Fahrenheit and Celsius to each other. Between Fahrenheit and Celsius, we've got 2 differences to contend with. One is the size of the degree. You'll notice that when I go from freezing to boiling water in Celsius, it's 100 degrees Celsius in terms, again, of temperature change. But it's 180 degrees in Fahrenheit as I go from 32 to 212. So to begin with, if I'm trying to do this in the form of an equation, I'm going to need to say that if I know how many Celsius degrees my temperature went up, to get the number of Fahrenheit degrees my temperature goes up, I'm going to need to multiply that by 180 over 100, right? It's going to be a larger temperature rise for Fahrenheit than it is for Celsius. Well, I can make that easier to look at if I simplify that fraction. It turns out they both have a factor of 20 in common, so I can say that a Celsius degree is 9/5 the size of a Fahrenheit degree. So that's one thing that's different. The other issue is the offset. And so in this case, what we know is that when I am at 0 degrees Celsius, the temperature is actually plus 32 Fahrenheit. So all I'm going to do to finish this equation is say that if I take the temperature in Fahrenheit, it's going to be 9/5 the temperature in Celsius plus 32. So in other words, if I'm at 0 Celsius, then this is just Fahrenheit equals 32. And then as I rise in Celsius, my Fahrenheit temperature is going to rise faster, because for every degree I go up in Celsius, I will go up 9/5 of a degree in Fahrenheit. Now that is slightly suboptimal. If we want to do it quickly, the way we do it essentially is what I just described, which is start at 32, but let's bite off bigger chunks of degrees than just 9/5. Let's say this: for every 10 degrees I go up in Celsius, 10 times 9 over 5 is 18 up that I would go in Fahrenheit. It's almost a 2-to-1 ratio, just a little shy of it. And so what that means is that if I start at 32 Fahrenheit, and that's 0 Celsius, if I go up to 10 Celsius, that's going to be 32 plus 18, 50 Fahrenheit. When I go up to 20 Celsius, that's going to be 32 plus 18 again. So 18 higher than 50, that's 68. 30 Celsius, another 18 higher than this will get me to 86. 40 Celsius, 86 plus 18 is 104. And so you can start to get a general sense of what some of these Celsius temperatures mean. Obviously 32 is freezing. 40 is a pretty nasty fever. 104 Fahrenheit, not a good spot. By the way, in the middle here you've got 37°C, which is body temperature, which in this scale would be 98.6, now that this scale has been tinkered with a little bit in the intervening years. 30 Celsius, 86 degrees, so this is a pretty muggy day. Right now, we'd probably feel like that was a little bit overwhelming. As I'm recording this in August, I would kill for a day that's only 86 degrees. 20, 68 degrees Fahrenheit, well that's just a nice day right there. That's almost room temperature. And 10 degrees, 50 Fahrenheit, let's just call that San Francisco, roughly 300 days a year. Now, as for the difference between Celsius and Kelvin temperature, the only difference here was the offset. So, while going from Fahrenheit to Celsius involved both multiplying the number of degrees by something and adding something to it, if Celsius and Kelvin are only different by way of an offset, then all I have to do is the addition part. And so that's all there is to it. The Kelvin temperature will be whatever it is in Celsius plus 273.15. So the Kelvin temperature will be higher. It's going to be in the hundreds of degrees most of the time that you're working with it. So armed with these two equations, let's head over to do a few problems.